In this screencast, we are going to continue to review information from General Chemistry 1 and 2, looking at covalent and ionic bonds. We're also going to hit Lewis structures as well. So I just want to remind you that a covalent bond is characterized by the sharing of valence electrons, right? And this happens between two or more atoms. In Gen Chem, we recognize this by two nonmetals, right? And so if you have two nonmetals, that's generally a covalent bond. Now, there's a few things that we need to think about here. One is there's a relationship between the distance between the nuclei and the total energy of the atom. Lower total energy corresponds to greater stability. So lower total energy corresponds to greater stability. Now, so for example, when you have two hydrogen atoms that are separated by a large distance and they are brought together, their total energy decreases when that bond forms. So you can see that here. Now, at one particular internuclear distance called the bond length, so that bond length is just the length between the two atoms, the energy needed to break the bond is that bond energy. So when we talk about bond energy, that's just the energy required to break the bond. Okay. Now, unlike total molecular energy, the higher bond energy corresponds to a more stable bond, okay? So a higher bond energy corresponds to a more stable bond. So this is molecular energy, this is individual bond energy. When we look at the formation of a covalent bond, and you can see that here, again, we're working with hydrogens. Each hydrogen has one electron. They come together, they form a covalent bond. We can think of the analogy here of a ball being at the top of the hill. It's naturally going to roll down a hill and become more stable. It's very similar here. These two, when they get together and they form a bond, they become more stable. So that's one of the analogies that we use. Now, it's really convenient. So if it skipped around there, it's because I accidentally skipped a head on a slide. And it might skip between slide 2 and 3. You haven't missed anything. But I just want to let you know there was a little skip there. I advanced too fast. So it's really convenient of us to think of a bond as a spring that connects two atoms, because we've got to remember that these two atoms are going to move. So the spring at a resting position here, we can think of kind of as a low energy state. But if we compress or stretch the spring, we are going to be at a higher energy state, and it raises the energy of the system. And bonds work very similarly, and you can see here how the internuclear bond distance increases, right, and the energy increases. So if those two atoms are really close together, then they're going to have higher energy. And if they're really far apart, they're going to have higher energy. But there is kind of this just right energy here where they have a lower energy and they're more stable. Now, we talk a lot about springs and things like this as oscillating, right? Going back and forth. And so I love practical applications of science. And one of the practical applications has to do with these oscillating bonds and the greenhouse effect. So when the atmosphere warms by greenhouse gases like carbon dioxide and methane, the reason we see that warming is because of the spring-like behavior of covalent bonds. Those bonds are going to vibrate at frequencies that correspond to that infrared radiation, and so they warm up. So in an isolated hydrogen atom, which we've been talking about this whole time for us, what we can see is that the electron is attracted to a single nucleus. In a covalent bond, the electrons are attracted simultaneously to two hydrogen nuclei. Now, this is going to lower the energy and increase the stability of both electrons. So when we ask the question, why is a hydrogen molecule more stable than two isolated hydrogen atoms? It's because the electron is attracted to two nuclei. So here we have one electron attracted to one nuclei and one electron attracted to nuclei. The reason it's more stable is because we have two nuclei here and the electron can be attracted to either of those. So that's what we see here. There's that simultaneous nuclei attraction. Now, you also, if you're a history buff, will have recognized hydrogen from the Hindenburg. So molecular hydrogen is very light gas, and it was used for buoyancy. And the Hindenburg was a commercial passenger airship in the 1930s. And because hydrogen gas was very flammable, the airship caught fire and was destroyed over New Jersey on May 6, 1937, and that killed 36 people. So that's where a lot of people kind of see his hydrogen gas historically. So just an interesting historical note there. Let's talk a little bit more about bonds. So if there was a little jump there, if it broke up just a little bit, it's because my cat tried to eat my pen. And so we had to take a quick break to extract the cat. So let's get back to bond length and strength. A few things to be aware of is that single bonds are going to be the most common type of bond that we run into in organic chemistry. They're not super duper reactive though, so they tend to be fairly uninteresting, unless there's an electronegativity difference, which we'll get into later. But what we find is that we are also going to have double and triple bonds. And really what we see is the main difference there is the number of electrons that are shared. So just as a reminder, a single bond, there are 2 electrons shared between atoms. A double bond, there are 4 electrons shared. And a triple bond has 6 electrons shared. A few things to be aware of is as the number of bonds between the atoms increase, the bond energy increases and the bond length decreases. Now we can measure bond length and energy too. So a single bond here is going to be the weakest and longest length, and then this will be a little shorter and stronger, and then this will be really, really strong and the shortest length. And so that's some of the things we're going to see. Now, in the next 2 slides, we're going to see a list of average bond energies for a variety of different bonding partners in organic species. Table 1.2 here is going to describe the bond energies for only single bonds. And you can look at this and see these are kind of typical bond energies. Then table 1.3, which is here, is going to compare bond energies and lengths for some common single, double, and triple bonds. Now, I do want you to notice here that you can see some energy differences, right? So a carbon-carbon single bond is 339 with a length of 154. The double bond now, we've increased the energy, 619, but decreased the length, 134. And then for a triple bond, again, we've increased the energy, 812, and the length is decreased to 120. We can see this same trend as we go from carbon-carbon to carbon-nitrogen, carbon-oxygen, nitrogen, and oxygen bonds. So this is a trend that we see through all of our bonds. Now, we're going to switch gears just a little bit and look at Lewis dot structures. To really understand a molecule's chemical behavior, it's really necessary to know about its connectivity, like which atoms are bonded together and what types of bonds, single, double, or triple bonds do we have. It's also really helpful for us to know which valence electrons participate in bonding and which ones don't. And so Lewis dot structures or Lewis structures are a really convenient way to share this information. So one of the things to be aware of when we talk about this is Lewis structures only take into account valence electrons. So we're only interested in counting up our valence electrons. The other thing to be aware of is that bonding and non-bonding electrons are going to be really clearly shown. Single bonds are going to be the sharing of 2 electrons, which you've already talked about. Double bonds 4, triple bonds 6. Each line represents a shared pair or a bonding pair of electrons. So each line represents a shared pair, which we can call a bonding pair of electrons. Now, non-bonding electrons are represented by dots. Right? And these are generally called lone pairs of electrons. Non-bonding electrons that are unpaired are represented by single dots. So if you have a single dot, right, that is an unpaired electron. And in chemistry, that's called a radical. And radicals have really specific types of chemical interactions that we can get to later. But if you see a species with just one electron, that's a radical. When you talk in biochemistry about free radicals, that's what they're talking about there. Now, what we're going to see for us mostly is we are going to deal with really just group 2 and group 1 atoms. So it's really important to understand that those are going to obey the duet and octet rule, right? So those shared electrons of a covalent bond count as the valence electrons of each atom involved in the bond. And so atoms tend to form covalent bonds to achieve this full valence, right? 2 electrons for hydrogen, 8 electrons for atoms in the second row. So hydrogen's going to really follow this duet rule. And then for the ones in the second row, we're really going to follow this octet rule. And so that's some of the things that we are going to look at. I forgot to talk to you about one other thing about radicals. So before we go on, I want to make one other note about radicals. Chlorine radicals, another place we see these chlorine radicals are in the stratosphere, and they catalyze the breakdown of stratospheric ozone. So if you have an unnaturally high concentration of chlorine radicals in the stratosphere, you can end up with an ozone hole. So we had that because there were synthetic coolants that were called chlorofluorocarbons, which are CFCs, and they were used in kind of the middle of the 20th century, and they led to the development of the ozone hole over the Antarctic. Now, those have since been illegal in the United States, and we've seen some recovery of ozone since then. Now, I want to draw your attention to some of the things that we've talked about with this image here. And so these are different Lewis structures. I want you to notice that hydrogen only has 2 electrons. So this hydrogen has 2 electrons that it's sharing with this hydrogen. I want you to notice that carbon can only form 4 bonds. 1, 2, 3, 4. Because it now has access to 8 electrons, and that's the octet rule. And so you can see that those 4 bonds can happen in a lot of different ways. We can have 2 double bonds. We can have all single bonds. And then you can look here at nitrogen. I want you to notice there's some lone pairs here. So all things that we see. I want to review the steps for drawing Lewis structures. So for example, you need to, here are the steps. The first step is you need to count the total number of valence electrons in the molecule. I want you to remember this is same as the group number, right? So some of the common ones that we're going to see is hydrogen has 1 valence electron. Carbon has 4 valence electrons. Nitrogen has 5 valence electrons. Oxygen has 6. Fluorine has 7. So we see these. For each ion, the negative charge increases the number of electrons by 1, and positive charge decreases the number of electrons by 1. So if you've got a negative charge, right, or a positive charge, you have to look at that and think about your electrons. Negative charge increased by 1, positive charges decreased by 1. Then you need to write the skeleton of the molecule, and you only want to show the atoms and single bonds required to hold them together. If the molecular connectivity is not given to you, the central atom is generally the least electronegative atom, and we're going to go into that in a second. You're going to subtract 2 electrons from the total valence electrons for each single covalent bond that's drawn in step 2. And then you need to distribute the remaining electrons as lone pairs. My suggestion is to start with the outer atoms and work inward. And also keep up with your valence electrons. You want to try to achieve a filled valence shell on each atom. So a duet for those hydrogen atoms, a octet for carbon, nitrogen, and so on. If there's an atom with less than a filled valence shell and you're out of lone pairs, you then convert those lone pairs from neighboring atoms into bonding pairs of electrons. And that's how we create those double and triple bonds. So we did this a lot in Gen Chem 1. This is really a review. Let's do an example. So we are going to draw the Lewis structure of HCO2- where carbon's a central atom. Now, if we didn't know carbon was a central atom, we could use electronegativity, but we haven't reviewed that yet. So we're going to do our first step. How many total valence electrons are there? Well, we have 1 hydrogen atom, and so that gives us 1. We have 1 carbon atom, and I'm going to look at the periodic table. I see that's in group 4. That gives us 4. We have 2 oxygen atoms. Each oxygen atom is going to have 6 valence electrons, and so that gives us 12. And then we have a -1 charge. And so that means we also need to add 1. We're going to take these and we're going to add them all up. And what we're going to see is we have 18 valence electrons to work with. And so the next thing, so we've done kind of that step 1. So the next thing we're going to go to is drawing the skeleton. So some questions you should ask yourself. How are you going to draw the skeleton? How many electrons must still be accounted for after drawing the skeleton? We are going to put carbon in the center because it told us that. And we're going to surround carbon with oxygen and hydrogen. Okay. Now, we've used up 6 valence electrons. So we started out with 18. We used 6 because there's 2 for each bond. So 2, 4, 6. When we go through and do this, that gives us 12 valence electrons that we still need, to be accounted for. So we are going to put those valence electrons around the remaining atoms to get an octet. And so I'm going to come down here. And so here's what I want to evaluate. Which things have a full octet or duet? Hydrogen has one bond. It's already got access to 2 electrons. It is fine. Carbon has 1, 2, 3 bonds. It still needs 2 electrons. Oxygen only has 1 bond here and 1 bond here, and so it only has access to 2. I need to make sure I have an octet for this oxygen, carbon, and this oxygen. So when I go through and I look at this, I'm going to put electrons around my outer atoms first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have run out of valence electrons, but I want you to notice that carbon doesn't have an octet. So what this means is I need to take 2 electrons from one oxygen and make a double bond. And so that Lewis structure then becomes this. Now, we've got a lot of great double checks here. First, we're going to check to make sure that each of these have an octet. So carbon has 2, 4, 6, 8 access to electrons. Oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. So those 3 fulfill the octet rule, and this fulfills the duet rule. It's got 2. Now, we also need to make sure and double check that we've used 18 electrons, and we can count 2, 4, 6, 8, 10, 12, 14, 16, 18. So there's our double check. We've used 18 valence electrons. Now, this is an ion, and ions a lot of time are shown with brackets with a negative charge. Now, if you showed this in a different way, you could also show this Lewis structure like this. This is a resonance structure, and we're going to get into more details about this later, but know that either one of these is fine, and we'll talk more about resonance structures in just a second. Now, not all atoms are going to have a complete valence shell, and some of them are going to be short an octet, and we call these a lot of times electron deficient, and that's okay. This occurs basically when there are not enough valence electrons to achieve a complete valence shell. And so elements in the third row also, well, let me back up. Before I get into that, some things that can lack an octet are things like boron. And if you have carbon with a positive charge, this is called a carbocation. So it's a cation, but it's carbon with a positive charge. Those lack octets. They're not the carbon with a positive charge, because it has that charge, is not super stable, but it will be something that we'll run into. The other thing that you can see is if you have elements in the third row or higher. Now, your book says in the third row or below, and that's really like by looking at the periodic table. But I want you to understand it's the third row, fourth, fifth, sixth, and seventh, right? That's all we're working with our periodic table. So if it's those rows, then they can have something called an expanded octet, where they can have more connections. First and second rows are never going to do this. We're never going to see this. But if you look at sulfur, for example, sulfur's in the third row, it can have an expanded octet, and that's what we see right here. So I'm going to write it in red. Atoms in the second row of the periodic table are forbidden to exceed the octet. Can't do it. So remember, in organic chemistry, we're kind of hanging out here in the second row. Now we'll have a few things that come along that are outside of that, but really we're here. Now, we can draw Lewis dot structures quickly in organic chemistry. And let's look at why. So in organic chemistry, you really are only going to deal with like hydrogen, carbon, nitrogen, oxygen, and some halogens. And so we have some rules that we can use, right? So that we make this fast, okay? So each type of atom tends to form a specific number of bonds and have a specific number of lone pairs. And so later you're going to learn that these number of bonds and lone pairs are really common because those atoms will no longer bear a formal charge, right? So each type of atom tends to form this specific number. So I want us to look at this. Hydrogen's only ever going to form one bond. It's not going to have lone pairs, okay, if it's uncharged. Carbon's going to form 4 bonds. Generally not ever going to have any lone pairs if it's uncharged. And those 4 bonds can look like this, 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 and this, always, right? As long as there's no charge. That's really, really important. Uncharged atoms. Nitrogen is going to have 3 bonds and 1 lone pair. Again, this specifically goes back to formal charge, which we talked a little bit about in Gen Chem, but we'll review again. That means nitrogen's going to have 3 bonds. They can be 3 single bonds, to a double bond and a single bond, or a triple bond and 2 lone pairs. Oxygen is going to form 2 bonds and have 2 lone pairs. It can look like this or this. That's what we're going to see. Halogens are only going to form 1 bond, and they're going to have 6 lone pairs. And then they talk about neon here. It's a noble gas. It doesn't really react, and it's because its octet is full. We're not going to mess with neon very often. So let's talk about how by knowing this, it makes doing Lewis structures faster. So we're going to look at this problem. It says, complete the Lewis structures for a compound whose skeleton is shown here. Assume that all atoms are uncharged. So if all atoms are uncharged, we can go back to those rules that we see. And so it says, look, which atoms other than hydrogen have an octet and which atoms don't? I'm going to highlight the ones, I guess I'm going to highlight in red. I don't know, maybe I'll highlight in purple. I'm going to highlight in purple, I think. Yeah, I'll highlight in purple. The ones that don't have an octet. And let's talk about how we do this. So first off, I'm going to look at hydrogen. Hydrogen only needs 1 bond. That hydrogen has 1 bond. That one has 1 bond. That one, that one, that one, that one, that one, that one, that one. All the hydrogens are happy, right? And so now I need to look and see what doesn't have its full octet. Well, I know for carbon to have a full octet and be uncharged, it needs 4 bonds. So let's look at the carbons, right? This carbon right here only has 3 bonds. That doesn't have a full octet. This carbon here only has 3 bonds. That doesn't have a full octet. This carbon only has 3 bonds, not a full octet. This carbon only has 3 bonds. And this carbon only has 2 bonds. None of those have a full octet. Now, look at this carbon. It's got 1, 2, 3, 4 bonds, full octet. This carbon, 1, 2, 3, 4, 1, 2, 3, 4. Those carbons are what we call happy. They've got a full octet. They're uncharged. We don't need to do anything with those. Okay. Now, so we've evaluated the carbons. We've evaluated the hydrogens. We have oxygen and nitrogen left. So when we look at oxygen, right, here, nope, here, right, that oxygen has 2 bonds, but there are no lone pairs that are shown. So remember from the previous table, oxygen's going to form 2 bonds and have 2 lone pairs. This nitrogen here only has 1 bond. From the previous table, nitrogen's going to have 3 bonds and 1 lone pair. So what we do now is we come in and we are going to put in the bonds and lone pairs to kind of fix this problem. right? So how many bonds and lone pairs are typical for each element? Well, I'm going to start at the top. Those 2 carbons that are there each have 3. If I put a double bond in between them, now those carbons have 4, right? And so that solves that problem. Same thing with these 2 carbons. I can put a double bond here, and now those carbons have access to 4. When I look at this carbon by the nitrogen, what I'm going to notice is this carbon only has 2 bonds, and the carbon on the left is already happy. I can't make any more bonds to that carbon, but I can put 2 bonds here and make that happy. Now let's flop over to the nitrogen. That means nitrogen now has 3 bonds and just needs 2 lone pairs to fit the pattern on the previous page. And this oxygen, 2 lone electrons on the nitrogen. Now this oxygen has 2 lone pairs, right? Or 4 lone atoms. And so that's what we can see there. So we now see that each of these follow the pattern and all have complete octets. And so if you need to commit that table 1.4 to memory, because it'll make this process go very, very quickly for you, and it'll give you double checks later on in organic chemistry. Now, we've talked a lot about covalent bonds, and these covalent bonds are really characterized by the sharing of electrons between 2 atomic nuclei. And we know from general chemistry that we can have 2 types of covalent bonds. We can have nonpolar covalent bonds and polar covalent bonds. And we want to review those now. So if the atoms are identical, then the electrons are shared equally, and that forms a non-polar covalent bond. Now, when we were in general chemistry, I said, hey, look, a lot of times it's easier to identify a nonpolar covalent bond because it's either going to be the same atom, right, or have a carbon and hydrogen. Now, then we could also identify nonpolar molecules if there was symmetry. But just for the bonds, those are kind of the 2 things that fall there. If the atoms are different, and the difference in electronegativity is big enough, that's over 0.4, then that will form a polar covalent bond. Okay, so the difference in electronegativity has to be over 0.4. So the ability for electrons in a covalent bond to attract, or the ability of an atom to attract, is governed by the element's electronegativity, which is represented with an En. Okay, so that's how we're going to represent those. Now, the next slide is going to show us electronegativity trends. And that particular scale was developed by a scientist named Linus Pauling. And atoms are going to range from 0 to 4 in electronegativity. These trends were measured and kind of given an arbitrary number. One of the things that you're going to notice, one of the things that I noticed is with kind of this new updated edition, in general chemistry, fluorine was like solidly at a 4, right? That's why we say it goes from 0 to 4. But when we look at this now, it's really going from 0 to 3.98. So that's kind of something that's interesting. But the important thing here to understand is that electronegativity values increase from left to right on the periodic table. So we're going to increase this way, and they also increase from bottom to top. So we're going to increase this way. Now, I've always told you to ignore the noble gases, and we can still pretty much sit with that, but I do want to show you now that some of these here do have a little bit of electronegativity. But for organic chemistry, the ones that we're interested in are carbon, nitrogen, oxygen, the halogens, so everything kind of in group 7. Sometimes we'll hit sulfur, sometimes phosphorus, second semester, nothing that we're going to worry about, and boron. So elements with the largest electronegativities tend to be in the upper right corner. right? So those things that we're interested in organic chemistry. And then things with small electronegativities tend to be in the left lower corner, okay? Cesium, barium, and so on. So the reason in organic chemistry we're interested in these things with really big electronegativities is because they form polar bonds. And it turns out polar bonds are reactive. And so there's some interesting chemistry that happens there. So in a covalent bond, electrons are likely to be found near the nucleus of the more electronegative atom. And they're less likely to be found by the nucleus of the less electronegative atom. And so we talk a lot about like kind of the evil big sister principle. If the evil big sister is going to break a cookie, then she's more likely to break off like a bigger chunk of the cookie for herself. That's kind of like electronegativity. This atom here has a higher electronegativity. It's going to break off more electrons. It's going to pull those electrons over. I want you to notice a few things. This means that this molecule has a bond dipole. So this creates a separation of positive and negative charges, which is called a bond dipole. And I want you to notice that the one that's the more electronegative is represented with a delta negative here. And we a lot of times will refer to that as being partially negative. You're going to notice over here, there's a delta positive, and a lot of times I'll refer to that as partially positive. You're going to see these most often in organic chemistry. You're going to notice here the cross and the arrow. That shows the kind of overall polarity of the molecule, and we'll see that less frequently, but it still will pop up. Now, I want you to notice that this is a polar molecule, right? It has a polar bond, and there's no symmetry. But I want you to look at these two examples here. These two examples are things that have polar bonds, but are non-polar molecules. And the reason they are non-polar molecules is they have symmetry. And so we've used symmetry as this big tug of war where we've got three hydrogens and we're pulling electrons in the three directions. We have carbon here and we're pulling the electrons out like that. So we've talked about this as far as in general chemistry, a way to identify molecules that are polar. But I want you to notice that, because sometimes there'll be these kind of sneaky questions that say which molecules have polar bonds but are not polar molecules. These have polar bonds, but because of symmetry, they're not going to have a net dipole, right? So let's look at an example. Okay. Identify the most polar bonds in the molecule shown here. Draw a dipole arrow along that bond to indicate the direction in which the bond dipole points. So when we look at this molecule, we need to think about what property of atoms should we consider to evaluate the bond polarity. Well, to answer this question, and let me choose a different color, right? We need to look at the electronegativity. Of each atom. Right? And so what we see here, when we look at the electronegativity of each atom is, for example, lithium here is 0.98, okay? And carbon here is 2.55, and hydrogen here is 2.20, and then oxygen here is 3.44. And so, of course, all the carbons are going to be 2.5 and things of that nature. So what we need to do is we need to look at the difference in the electronegativity values. And you do this by subtracting. So, for example, if we want to look at the difference in electronegativity of two atoms, so let's look at the difference between the carbon and the oxygen. So we're going to look at the difference between the carbon and the oxygen. So right here, this kind of bond right here. When we look at that, I'm going to say, okay, I've got 3.44, and I'm going to subtract 2.55. And that difference, if my math is right, is 0.89. So that's one type of bond that's in this molecule. Now, we can also look at the difference between carbon and hydrogen. Those are bonded. And when we look at that, we see it's going to be 2.55 minus 2.20. Doesn't matter which, you just want to put the bigger one in front, right? Because we're looking at difference. That's all we're looking at. When we look at that, we see that it's 0.35. Okay, that's the difference there. For something to be polar, that difference has to be 0.4 or greater. So we would consider this to be a nonpolar bond. This is a polar bond, right? But now I want us to look at this lithium and carbon. When we look at lithium and carbon here, that's going to be 2.55 minus 0.98. And that ends up being 1.57. And so that one has the greatest dipole. And so we would consider it to be the most polar bond. And so we're now going to draw a dipole arrow along that bond to indicate the direction in which the bond dipole points. When we do this, we start for the one that's the least electronegative, which is the lithium, and we're going to draw to the carbon, which is the more electronegative, and we kind of leave a plus here at the lithium. So we draw an arrow to the carbon, it's more electronegative. That arrow is showing where the electrons are being pulled to. And then that kind of positive there on the lithium indicates that that's the partial positive. And so that's how we draw that. Now, one of the things that we can use to illustrate the distribution of charge along a covalent bond is something called an electrostatic potential map. And so I want to show you some of these. An electrostatic potential map is going to show a molecule's electron cloud in colors that indicate its relative charge. I want you to notice that red corresponds to the buildup of negative charge. So red is going to correspond to negative charge. And so what you're seeing here is hydrofluoric acid. It's a polar molecule. Fluorine is more electronegative. It gets the delta negative here. Hydrogen's more positive. It gets the delta positive here. And so if we look at this in electrostatic map, you can see that the red here is with fluorine and it's got more electron density or is more electronegative. We use blue as to correspond to a buildup of positive charge, right? And so you can see here that we have a lot of positive charge. Now I want you to notice here, we've got some kind of greens and yellows. You're going to see that when there's not a huge difference between positive and negative, right? Right here in the middle, not a big deal. So we can look here and we can see that even though carbon dioxide has some polar bonds, they're gonna pull and even out a lot of times. And so that's one of the things that we can see there. Now, kind of the last thing we're going to do in this screencast is talk about ionic bonds. And so rather than sharing electrons, the more electronegative atom acquires electrons by giving up the less electronegative atom, and it kind of forms these oppositely positive charges. And so when we looked at lithium before, that was an ionic bond. So when elements in a compound have a large enough difference in electronegativity, an ionic bond can occur. And so that's what we saw with lithium. That was a really big difference in electronegativity. So most of the time, how we define this in general chemistry was a metal and a non-metal. And really, that's just a really easy way to identify it, because the difference between a metal and a non-metal gives us that big enough difference in electronegativity, okay? And so you really need to be able to recognize this because we are going to deal with a lot of ions in organic chemistry, and you need to be able to recognize what their counter ions are. And so what do I mean by that? What do I mean by counter ion? Well, if something's ionic, and for example, we're dealing with hydroxide, and we want to add hydroxide to a reaction, we can't just go and get hydroxide all by itself. We have to add sodium hydroxide. And so the sodium here would be considered a counter ion. Okay. But we can recognize these because they are all, they have charges, or they are positives and negatives. And so we can see that these are ions and they form ionic bonds. A few things to kind of keep in mind here is these ionic bonds are formed by the electrostatic forces between anions and cations. So sodium chloride is a really good example. While covalent compounds are generally found in discrete uncharged molecules, the ions in ionic solids are going to be arranged in a regular array called a crystal lattice. And that's something that you can see here represented. So this would be an example of a sodium and chloride crystal lattice. Polyatomic ions contain multiple covalent bonded atoms and usually consist of only nonmetals. A really good example of that, right, is NH4+, that's ammonium. My suggestion is to review your polyatomic ions if you have forgotten them, and I can post that sheet again. But other ones that we see really commonly are ones like hydroxide, which is shown here, okay? This is a methoxide, which is shown here. So this guy right here is called methoxide, okay? And methylammonium, which is shown here. So all of these are really common polyatomic ions. So again, the best way to identify an ionic bond is to look to see if it's a metal or nonmetal, with ammonia being the exception. So in this screencast, we've reviewed covalent ionic bonds and Lewis structures. Looking ahead, we're going to start looking at some formal charges and resonance structures.